Welcome back, team. So we're going to continue on with the fractal topic, but now I'm going to talk to you about how to compute the dimension of an object which is not necessarily self-similar. So what we talked about before was how to compute the dimension of an object that was self-similar. So in the case of the Sierpinski triangle here, what we did was we looked at scaling the length down, and we saw that if you scale the length of it down by a half, you get a perfect copy of the same thing, but it would take three of them to make up the whole that we saw at the beginning. So we had this length scaling factor that was equal to a half, and this mass scaling factor that was equal to a third. And so with 1/2 equals 1/3 to the dimension, we got that this dimension was equal to 1.585-ish. But that doesn't scale particularly well to the general idea of fractals appearing in nature, because the fractals that appear in nature don't have this perfect self-similarity. And so now I'm going to talk about how to compute the dimension of an object using not self-similarity, but using a technique called box counting. And this is precisely what it sounds like. We are literally going to count boxes. This dimension is sometimes called the box counting dimension. But it's fundamentally the same concept, but it breaks the necessity for self-similarity. So if we don't have perfect self-similarity, how do we compute the dimension of an object? So I'm going to start with this circle here. Let's say that we have this circle and the whole thing's filled in. We want to know the dimension of the circle, or at least we want to verify that the dimension of the circle is 2. So you can imagine putting this on a grid, and you're going to have to just bear with me and imagine that these are perfectly spaced grid lines, and they won't be. Okay, so what's going to happen is we have this grid, and you have to imagine that all of these spaces are perfectly square boxes. And we want to think about how the number of boxes that are touched by the circle would change as we scaled the circle up. Now, in the case of this circle that's perfectly filled in, we would hope that the number of boxes it touches is roughly equal to pi r squared, because that's the formula for the area of a circle. And so we need this to be, so this is what we would expect to be true. And this is if the radius of the circle is measured in box lengths, of course. So from the area formula of a perfect circle, we can get an estimate for the number of boxes that it touches at each size as we scale it up. But what this means, in what we care about in this case, is the proportionality. So we don't have to worry about the pi, because the pi is just this constant prefactor. And so what we care about in this case is the fact that n, the number of boxes being touched, is proportional to r squared. And so this concept is precisely equivalent to the same thing, but if you consider making the grid finer as opposed to making it bigger. So if we wanted to double the size of this grid, all we would have to do is, if we wanted to effectively double the size of this circle, all we would have to do is cut the size of every grid box in half. So we would put new lines down the middle of each of these columns, and then also down the middle of each of these rows. So actually each box has been, each box's length has now been cut in half. So we have boxes that are now half the length that they used to be. And so the point of me showing you this is that we can actually rewrite this proportionality equation to say n is proportional to 1 over s squared, where s is the side length of a box. Okay, so what this means here is that, and I'm just gonna make some room over here. I'm gonna rewrite this last line because this is the line that's important to us. So n is proportional to 1 over s squared. So what this means is that if we plotted n against 1 over s, so it's like we make these grid boxes smaller, we count the number of grid boxes, and we put down a dot for the number of boxes that touched at that side length, n versus 1 over s. So we plot 1 over s on the x-axis, and what we should get is something that perfectly fits to a parabola with some prefactors. So this would be, we would get some line that shows that n is equal to a, which is some number that we don't really care about, times 1 over s cubed. Or not cubed, squared. So this should be true. This will be true for this circle because the circle is dimension 2. But what happens when you apply this same technique to the Sierpinski triangle is you'll get I'm just going to rewrite this here. D equals 1.585. For this one, if you did the same thing, you make a bunch of different grids with different box sizes. If you plot n, the number of boxes that are touched by the Sierpinski triangle, over 1 over s, you should get, again, something that curves upward but not as fast. This is a line that you fit to a bunch of dots. And this should be equal to, or this line should be generated by the equation n is equal to some a times 1 over s, but to the dimension 1.585. So again, just to reiterate, you make a grid all the boxes are the same side length. You record the side length, you record the number of boxes that are touched by the shape, and then you put down a point, and you do that for a bunch of different grid sizes. What you should get is something that has this shape. So that's all fun, but it doesn't seem that practical yet, because how do we fit a perfect curve to a line that just has some power that we don't know? And that's a good question. So I'm going to show you how this works now in more of a practical way. Okay, so we have the following equation. We have n number of boxes touched by the shape is equal to some number times 1 over s to the dimension. So this is number of boxes touched some number that depends on the shape in question, but it doesn't change the dimension. And then here we've got and this is side length of box. And this is the dimension. And what's useful about this relationship is that we can actually change this into something that's much easier for us to model by taking the logarithm of both sides. So what I mean by that is literally you put both sides, the left-hand side and the right-hand side of this equation, inside a log. And you can do log base anything, but probably log base 10 is easiest for you to think about. So we do log 10 of n equals log 10 of a times 1 over s to the d, like that. So this was literally, we just took both sides of this equation. Both of them are now inside a log. Okay, now we can apply a bunch of transformations to this. We can apply a bunch of transformations to this side that make it much easier. So we're going to do that. So we'll have still log 10 of n on this side, but this side, log rules tell us that if we have two things being multiplied inside a log, that they split up into separate logs that are being added. So this is equal to log 10 of a plus log 10 of 1 over s to the d. And now lastly, log rules also tell us that if we have log of something that's raised to a power inside the log, that's the same as this power coming down and just multiplying the whole thing, and the power inside the log turning into a 1. So this is equal to, so log 10 of n is then equal to log 10 of a, again that's just some number that's not changing, plus d times log of 1 over s. Now this is a super useful relationship, and actually so useful that I'm gonna square it off in 2 different colors. And now you're asking, Ben, why is that useful in any way? And so I'm going to tell you why that's useful. And I'm going to tragically have to erase my Sierpinski triangle that I spent an embarrassing 15 minutes drawing. The reason for this is that we can actually, using this relationship, we can plot, we can change our n versus 1 over s plot into a linear relationship by plotting instead of plotting n versus 1 over s, plotting log n against log 1 over s. And so what happens here is that this relationship, if we consider each of these to be our variables, our input variable is this whole thing, log 1 over s. Should have a base 10 there. Log 1 over s. This is just a number. Just a number, a constant number, it's not changing. This is our dimension, which also doesn't change. So there is a linear relationship between these two variables that has a slope of the dimension. So if you count up your boxes at a bunch of different side lengths, what you're going to get is a line, and then that line is going to have slope equal to d. So what you can do here to kind of wrap up this whole process into lesson into one process that you can carry out on your own. Let's say that you have a shape and your shape is like the edge of a coastline, and it kind of does this. And as you zoom in, the roughness continues. You continue to see more and more roughness as you zoom into these things. It doesn't really get smooth as you zoom in. So you cover it with boxes. They're all the same size, even though I'm drawing them haphazardly and you can't really tell that they're all the same size. They are, trust me. And you have some side length of each box, so side length s, and then what you want to plot is log n versus log 1 over s. And so you count up the boxes that are touched. You go 1, 2, 3, 4, 5, 6, whatever. You get some n. You take its log. You take the log of 1 over s, and then you plot a point. And then you do the same thing, but you make the grid size different. So now the boxes have a different side length. And so with this new side length, you count up the n, you count up the number of boxes that are touched, and then you take its log, you take the log of 1 over s, and you plot your next point. And then you keep doing that you take a line of best fit. This line's slope, and this line's slope is equal to the dimension of this coastline. And so at the end of the day, you have this simple process of counting up boxes of different sizes, plotting them, doing a quick linear fit, and then finding the slope, finding the dimension based on the slope of that line. And that is box counting dimension. And this is the way that you would compute the dimension of any sort of shape, regardless of whether or not it's a fractal, or regardless of whether or not it's a fractal, regardless of whether or not it's self-similar. This is how the shape of that bifurcation, or the dimension of that bifurcation diagram that we saw earlier, would be computed. So when we were doing chaos theory, we had this bifurcation diagram that had these forks in it. You did this in class, just plotting several individual points. And then you kind of got this crazy mess. But then it had kind of breaks of order in it. And this is also a fractal that also has a fractional dimension that you could compute using this same process. So box counting dimension, universal method of computing the dimension of shapes, including fractals.